So it's a real pleasure to be here and talk about transformers and reinforcement learning. But there is one problem that the topic is very huge, and due to the time constraints, we can't go very deep into this area of reinforcement learning and calculated robotics. So I hope this talk will be like a good introduction, or maybe first jump into this area. Then if you want to like go deeper into this research, you can find there to navigate, where to find these ideas. Okay, I'll start from like short description of reinforcement learning problem. So the main idea here is that you have an agent that interacts with the environment by applying some action to this environment. And environments, or maybe interpreter, returns you reward. This is like a scalar number or a scalar signal, how good was this action or how bad it was. Or it can return also state or observation. So the difference here is that if we're talking about fully observable environment, and we know the whole information about like state of an environment, then it's state. But if the environment is partially observable, for example, as an AIRI game, then we call it observation. So having this in mind, each time step we can characterize by observation, either state, action, and return. And the whole goal of the agent to maximize expected reward, applying some actions in the environment. Of course, the problem formulation is very common, and we have to find the places where I can apply transformer models. And as you can see here, there are several places. First of all, of course, you can learn the policy using transformer models. Then you can model environment and learn the world models to simulate the environment. And if you notice here, there's like some models, some names that I put here. And some of them appear both in the policy and the world model. So it's not very simple, and it's even not possible sometimes to split these two parts. But sometimes you can do it. Also, you can design a reward using transformer models. And of course, you can use it to find and to obtain useful representations, such kind of using visual transformers or large language models. In this talk, I won't tackle this part, and just give some examples for another areas. Again, in this talk, I will concentrate on 3 domains. Game environment, so it's usually like AIRI games. Then the observation fits to the agent. It's usually like screenshot. Then we will talk about control environments. Here, it's not observation states because the concrete environment state is scripted as a joint angles of some creature or some model. And also we'll talk about robotics, either in simulated environment like Weimar, with this moving arm, or applying it to real observations from the real robots. And also have to do like final remarks before moving to some particular models, that reinforcement learning is kind of like sequential decision making. And most in this talk, I would talk not about reinforcement learning itself, but about its offline variant. Then we don't interact with the environment while updating our policy, but we have a predefined data set. So this is trajectories. So starting from the time step 0 to the time step capital T, we record these trajectories and use it as like in classical supervised machine learning. Even though when we move to robotics, we'll talk about behavior cloning. So the difference here for us, very simple. We just skip rewards. So we have observations and we have actions, what we will take. Okay, having this in mind, let's move to the policy learning. And I'd like to start with decision transformer. This is quite old model, but I think it helps to flourish the whole area of applying transformers to offline reinforcement learning. It's very simple in its idea, but it's very powerful. So in the core here, there's normal causal transformer. So the word causal means that we can look in the future and predict current action just looking at this history, not looking at this forward part. And usually, if you talk about transformers in NLP, the nature of tokens are identical. They came from the text, the corpus of text. But in decision transformer, we used 3 different types of tokens. First of them is this R capital hat, and this is actually return to goal. This is cumulative reward on the whole trajectory, but not discounted. So just sum up whole reward. This is kind of desired reward, what we want to get at the end of the trajectory. And every time step, we will decrease this amount by immediate reward we are obtaining this particular step. Then we have to encode state or observation somehow. As I said, in AIRI games, it will be pictures, like screenshots. But in the control task, it will be a vector of numbers. And there is also an action. For AIRI games, it's discrete actions, just like move left, move right. For control tasks, it's again number of vector of numbers with concrete differences in joints in some particular places. It predicts next action autoregressively, just like normal model, transformer model, and get a good results on AIRI games and also on the control tasks. Like more or less, like in most environments, it's the best, but not everywhere. But the one problem here that the transformer has a fixed context length, and we cannot extend it unboundedly because of quadratic complexity. So you have to stay in this context. But in some environments, it would be a good choice to use much longer context length. And here came some ideas from the natural language processing, such kind of like transformer XL or recurrent memory transformer. And this is actually our current work, what we're working on. It's like recurrent memory decision transformer. And the idea here, so we have almost the same transformer, but we have these memory embeddings. This memory embeddings that helps us to transfer some information, then the context passed away here, but this information will kept in the next context chunk. And using these modifications, we show more or less the same result with, as a decision transformer. Our more recent model we will discuss next. But we outperform decision transformer and its variations on control, on game environment tasks. But the one feature of these models, what we predict just one action in a step. So we cannot plan the whole trajectory. So we have to somehow interact with the environment in the evaluation mode. But what if we want to, like given the initial state, we want to predict the whole trajectory, the whole plan, and maybe we want to predict several plans, and then choose the best one and apply it on the real agent. And here comes the trajectory autoencoding planner. Actually, in the time of the decision transformer, there was concurrent work called trajectory transformer, and this is like extension and modification of this work. And idea here that, first of all, let's learn some latent action space, predict in this latent action space, and even more, if you have a huge dimension of like in real action space, this latent action space may be much smaller, and it will be simple to predict next action and do it much more efficiently. How it's done? Having this initial trajectory, again, we're still working with offline data. We take, okay, let's go on. Yeah.
So in this trajectory, you have rewards.
Yeah, definitely.
Right? So it's not
this V here is actually turn to go. It's but it's the picture from the original paper. They somehow changed it to be.
Okay, so you need to have R in your data somehow.
Yeah, but if you work with offline data, offline RL, you usually have it.
I see.
Yeah, but if you're talking about behavior cloning, you don't have reward. But in offline RL, you do it.
Can you give one like dataset example where you have it?
AIRI 100K.
Okay, so in
Or
Atari,
D4L.
it's always you have the score.
Yeah, yeah, yeah.
I see, I see.
And D4L you also have this data. So given this initial x1, this consists of state, action, immediate reward, and this v with actually turn to go. We use encoder to encode it into sequence of tokens, more or less meaningless. Tokens, we encode it, then they do pooling just to shrink the number of the tokens, and use vector quantization encoder to learn new tokens in this latent space. Then using these Z tokens, they again tie linking to match the input size, concatenate initial state conditions, and pass it to the decoder. And then they decode the whole trajectory. So starting just from this part, they encode the whole trajectory, and you can apply this trajectory on a real robot. And as you see here, you cannot split the model and the policy, because here you have to predict the next state. But then we trained how we will apply it. Well, it's the simple part. We just sample somehow initial embeddings, decode them into trajectory, and then choose one of this trajectory depending on the evaluation criteria. The criteria is very simple. First of all, we sum up the whole reward until on the whole trajectory. And this is depicted in red. And the blue part penalizes us if we apply some out of distribution actions. So if this probability of these tokens are very small, and we can adjust it by this threshold, when we just don't use this trajectory. Well, this is just like a simple vanilla sampling, but we can apply here techniques from natural language processing and use beam search. Then we extend our trajectories iteratively. First of all, we do capital B initial trajectories, evaluate them, keep capital B best trajectories. Then to evaluate them, we have to decode them to the real actions. Then they again taking this capital B trajectories, expand each of them to be more trajectories, and repeat the process. And finally, we choose one of these capital B trajectories and apply it on the real agent. If you see the results on the traditional contour task, the decision transformer was tested. There is no huge advantage of applying this particular model. But if we move to the another task, a kind of like robotic hand control, there the action dimensionality increases. We will see what this planning in the latent space give you good results. And here the graph, here's the plot how TAP model behaves compared to the another common models such as trajectory transformer, CQL, if we increase the number dimensionality. Yeah.
Can you explain I guess those are some metrics that, or I guess not everybody knows what they are. I mean, TAP, TT.
Yeah. This okay. Well, this is just performance of this TAP model divided by the performance of the TT model. So they just like that. And
how
this
is the performance measured?
scores, just scores. How I think how many steps you need to do this task. But in the previous part, we've seen then we both model the world, the environment, and also learn policy. But we can just learn the world model of the environment. And this is one of the recent work called AIRIS. And the idea here that let's train our agent only in imagination, only using the world model of the environment. And then they compare the results to the Atari 100K datasets, which is limited to 2 hours of real-time playing with the in-game. So it's not huge dataset, just 100,000 iterations in the environment. How do they do that? First of all, we receive x0. This is the initial state, actually it's initial frame of the game. Then we use encoder to encode it into a sequence of tokens z1, zk, and decoder to reconstruct it in the predicted state. So the idea here that the x0 and x hat 0 should be identical due to some error. Then using this predicted state, we can use policy to predict next action. And then having this action, this latent tokens of the state, we use transformer model G that predicts us reward on this time step. Is the state terminal or not? And also it predicts the next tokens which we will decode later into the image of the next state. And the interesting part here, that the interaction with the real environment happens just that's here. And after that, this is like done in the imagination, in the word model. And the authors use real interactions with the environment only to update this word model G, encoder and decoder. But the whole policy learned in imagination. And there's interesting results. So here the 4 trajectories which were decoded from the one initial state. This is like a real state. And you can see that trajectories are different. And even though the enemy appears like in the right part of the screen, like not somehow pop up in the middle randomly, and even they can predict different number of enemies. And the very important part here that if you kill the enemy, it disappears from the environment. So the model is capable to learn it. And if you look at this example with Pong, on the top there is a test trajectories, real interaction with the environment that we can collect. On the bottom of this is generated trajectory. It's generated from these 2 initial states. And you can see that these images, these frames are almost identical. And even the model learns to increase the number, increase the score if you win the exchange. So this is very, very important dynamic of this environment. And as I said, and after stated, they beat on many environments other models. So compared to this limited number of interactions with environment. Okay, now let's move to the reward design. Usually, if you want to somehow design the desirable behavior, you have 2 choices. First one, we can manually design some function using our knowledge of domain. Another variant, we can, if we have a lot of data, labeled data, we can use it and learn it like usually in supervised learning. But what if you don't? If you have some examples labeled, but how can you use it? And the authors says, okay, let's use large language model. Why not? They tested on a very simple environment. This kind of textual game called Deal or Not Deal. And the idea here, the 2 agents, Alice and Bob. Alice and Bob have to split items among them. They have their own preferences to some items rather than another. And Bob has a fixed policy. But our goal is to learn Alice policy. How do they do it? First of all, they say that the Alice may have several different strategies. One of them may be versatile. So the Alice never propose the same splitting. Then they describe this environment as a prompt, some return of the concrete episode, move it to LLM, and say, is Alice versatile or not? The LLM can answer you yes or no, and then we transfer it to a number and use this number as a reward signal. Feed it to the agent. Agent updates, it waits, depends on this reward signal, and unroll one more episode. So this is actually the episode the agent plays. Then we take this episode, put it in the prompt, add question, right, using some parser, and then again put it to large language model. And do it repeatedly. But it was training. In evaluation mode, they just sample some episodes of the agent and evaluate if this agent learned particular behavior it was desired to. And here are some results. So they had 4 different behaviors, like versatile, pushover, then Alice gets less, tends to get less score than Bob. On the other side, Alice gets more points, and stubborn, then the Alice gives the same proposal every time. And also they, as a baseline, they use simple self-supervised learning, just supervised learning. Just simple model that predicts you 0 or 1, depends on the input data, like kind of MLP. And first, they see if the labeling accuracy of LLM is good. And the one point here that the supervised learning algorithm uses here the same number of examples as was given in the prompt to the LLM. And you can see that LLM outperforms this huge amount. LLM is pre-trained, it's GPT-3. Yeah, of course, there's the kind of, we can use a simple MLP as supervised baseline and huge GPT-3, but it's a current trend. So even there some questions could arise. And after that, they check if a real agent that we train actually learns the behavior. And as we design this manually, we can compare it with a true reward, which is usually not available in practical tasks, but still in this work, they use it. And you can see, again, using supervised learning is much worse than proposed model. Well, but this is seems like a trivial result, because if you have this bad reward signal, you'll get a bad result at all. And then let's move to robotics. Here I just want to briefly show 2 models that are kind of highlight the trend, the current trend in applying large language models. I think we agree that large language models are transformers, so it's fit in the topic of this lecture. And one of them is Palm-E. And idea is very simple. Let's use large language model as a high-level planner. But models have to know something about environment and use feedback signal. So for this feedback signal, they use images. And again, here we can use transformers, such kind of visual transformers, to represent input images. And then, given a description in a natural language, for example, sort colors into corners, and given the initial image, the model can predict the actions, high-level actions, described in natural language. Like step 1, push the green star to the bottom left. Step 2, put the green circle to the green star. The tricky part here is that you somehow have to transfer these high-level actions to the low-level actions of real robot. And this work actually is done on top of the say-can work and interactive language environment. There you have this already learned policies that helps you to transfer these texts to exact actions of a robot. But as an extension of this work, there's another model from a current model, it's months ago just appeared. And here they use in the core Palm-E, or another variant of visual linguistic model. But here, they predict not the high-level actions, but exactly low-level actions which could be applied on a robot. So I think this is very interesting work, and they show interesting results. But there is actually a problem with comparing results in robotics. This model are not available. You cannot run them. Even if they would be available, 540 billion models is quite difficult to run. Yeah, but without this, different labs may have different robots. And of course, there's some common models such as UR5, but nevertheless, there could be different robots. And the environments, even if you have the same robot as in a nearby lab, the environments may be different. So it's maybe different light conditions, different table, whatever. And even though if you have this all in common, maybe there could be different objects. Because if you want to move a chocolate bar from the one place to another, maybe on the other part of the world, there's another chocolate bar, and you can find the same. And this is really complicated the benchmarking current models, because you have some model, it behaves well, but you don't know which results, how to compare them. And I think now it's made a really huge step towards solutions of these challenges. There are at least two works recently proposed that made a lot of work for us. They have a robot. This one work is this three-finger robot, and another one is just ordinary arm robot. They collected data. This is again offline data. This collects for us, and we can train our model and send to these labs, and they run our policies on these robots, and you can evaluate it. And the difference here that in this data set they used a lot of data, but there are no pictures. They're just torques, angles, velocities, some pressure sensors on this tip of the fingers, but no images. In this data set, there are images, and there are also depth, estimated depth from camera. Even though this is behavior cloning, but there is a reward. But the problem here that reward is distributed, and you get just at the end this reward as the amount of material while scooping or pouring, so this in grams. But nevertheless, it's a very interesting topics, and you can now really train a policy, send it to a lab, they evaluate it, and you get the result.
So you send them your code?
Yeah.
And they are...
and they run it on a robot, a real robot. So it takes some time. They can say, okay, maybe 72 hours.
Wow.
But actually, from my experience, we sent some policy to this lab, but we're still waiting the answer. It was 2 months ago. Well, there could be some problems.
Ask for money or?
No, it's free. They just work for the whole community of researchers. I think it's very
Generous.
Yeah, that's true. I mean, it's because it's this is quite simple because you have this closed box, and there's a robot and there is one cube. But here you have to pour, you have to scoop, and something is messed around. You have to clean it and redo next episode. No, move to the next episode. Okay, actually, we came to conclusion. And here I just want to highlight that transformers could be used in reinforcement learning in different parts. I think you can combine them even more and find new combinations. Another one is large language models is really trend in robotics, and especially in embodiment, artificial intelligence, what I'm currently working on. And happy to us, benchmarking on real robots begin to appear. So maybe in the real future, we can compare our models better than it was done before. That's it. Thank you for your attention.
I'm not mistaken, you say that you can extract policy of agent or not?
From what?
Determine the policy of agent. If I
You mean in this last part?
I don't know if you say that thing. Or
No, I mean, you can learn this policy, yes? And of course you can design some policy, like handcrafted policy. But what do you mean by like extract?
policy,
Huh?
to determine policy.
Yeah, you can determine,
If we have many
some
policies,
deterministic policy, yeah. Did you answer the question?
if you have many policies,
Yes.
You can determine what policy is now working.
Maybe you can have some proxy, depends on the score. Yeah, you know, if the score is bad, the policy is bad. If the score is high, the policy is high. But I don't see then this problem could appear. I mean, then this task. So, then you need actually to. It's kind of, I think.
It's only a question.
Yeah. No, I mean, so if you have several policies, like you don't pick one particular, you just, or maybe you meant this trajectory planning. Then yeah, but the policy is the same. Trajectories are different. So policy is the same. Yes. Oh, that's it. Thank you.